Good afternoon, everyone. I'm Ke Xiao from College of Engineering at Peking University. Today, I will be presenting our recent work on the application of deep neural networks for efficient chemical source integration in ammonia and hydrogen combustion simulations. Hydrogen and ammonia are emerging as promising fuels for zero carbon energy solutions. Hydrogen is sustainable and emission free, but poses challenges in storage and transportation due to high diffusivity and reactivity. Ammonia, as a hydrogen carrier, on the other hand, has the advantages of easier and safer storage and transportation, but suffers from low reactivity and high NOx emissions. Combining hydrogen and ammonia offers a balanced solution, enhancing combustion stability and reducing emissions, aligning with sustainable development goals. This also calls for further research. Turbulent combustion modeling is crucial for gaining deeper insight of ammonia and hydrogen combustion and further optimizing combustion systems. By nature, turbulent combustion involves complex multiphysics problems, which are often modeled using non-general assumptions. However, usage of detailed chemical reaction mechanisms provide comprehensive statistical representation of reaction processes without modeling assumptions, and thus result in better applicability and versatility. But they are also computationally demanding and can require millions of CPU hours for a full-scale LES combustion simulation. When using detailed mechanisms in combustion simulations, the computation bottleneck is often the integration of stiff chemical ODEs. The many species and multi-scale nature of chemical kinetics often result in large-scale stiff ODE systems, which can consume up to 90% of the total computation time. This raises the need for acceleration of these time-consuming ODE calculations, and also raises a more specific question of the potential of machine learning methods for solving these stiff ODEs. Recent studies by Ding et al. And Redshaw et al. Have explored using deep neural networks to replace direct integration of chemical reaction source terms. Their approaches involve manifold sampling and training artificial neural networks to predict changes in species concentrations. Zhang et al. Employed multi-scale sampling to train DNNs on large datasets, achieving good generalization and demonstrating the potential of machine learning methods in accelerating combustion simulations. These works showcase the potential of machine learning methods. However, there is still room for improvement in generality and usability. Our team proposed a method we call DFODNet. It provides a consistent approach for developing DNA models to replace chemistry integration across different fuels and flame configurations. The idea is to generate training data from low-dimensional canonical flames and enhance it through random perturbation and augmentation to meet the requirements of fully three-dimensional simulations. This method's objective is to achieve high accuracy, good generalization capability, and satisfactory computation speedup. I will proceed to introduce this method from these perspectives: our computation platform, the generation process of training data, and then model architecture and algorithms, and at last validations. Our DFODNet method is integrated into DeepFlame, an open source CFD software platform for deep learning assisted reacting flow simulations based on OpenFOAM, Cantera, and PyTorch. It supports single or multi-phase, laminar, or turbulent reacting flows at all speeds. Current key features of DeepFlame include machine learning-based acceleration of different procedures in the simulations, including calculations of chemical source terms in this study, and also thermal physical properties, and also GPU-based acceleration of model inference and PDE solving. For our generation of training data, we collect thermal physical base states from a series of carefully designed canonical flames. For example, one-dimensional laminar premix flames with different equivalence ratios and two-dimensional counterflow diffusion flames with different strain rates. The simulations of these flames are also performed using deep flame and are highly efficient due to their simplicity and low dimensionality. These thermophysical base states present a basic level of resemblance of our target three-dimensional problem and become our starting points for further data augmentation. We use random perturbations along with range limitations of heat release rate and element ratio to simulate the effects of high-dimensional turbulence. We also perform data covering assessments to provide insight of hyperparameter and model size settings in the training process. This approach ensures comprehensive dataset coverage for training. Our DNN models receive inputs of temperature, pressure, and species mass fractions pre-processed using the Box-Cox transformation. We use a Galou activation function and a multilayer perceptron with 3 to 4 hidden layers to get outputs as changes in species concentrations over time. The model incorporates physical constraints such as element ratio and enthalpy conservation to ensure realistic predictions. This approach, as demonstrated by Ding et al. And others, enhances the model's inference ability while minimizing non-physical phenomena. We utilize various flame configurations to establish a standardized model validation procedure aside from single point tests. This includes priority tests like one-dimensional premixed laminar flames and two-dimensional counterflow diffusion flames, which we sampled from, and also posterior tests such as two-dimensional planar jet flames and two-dimensional homogeneous isotropic turbulent flames. Also, in previous works, we also validated against a full-scale LES of the Cambridge burner. For a glance at computation speedup, we compared the performance using 16 CPUs versus the addition of one NVIDIA GPU for mechanisms involving 24 species of ethylene, 41 species of kerosene, and 19 species of methane. The results demonstrate that our method ensures adequate precision while significantly speeding up computations. This slide illustrates the flowchart of the DFOD method to sum up our previous discussion. We start with generating training data from low-dimensional flames and then go through data augmentation procedures and then train DNN models for large-scale CFD simulations. This is a systematic approach that aims to ensure efficient data generation and robust model training. In this work, we tested our method on turbulent partially premixed jet flames developed at Cost University, namely Flame D and Flame F. Here we show a schematic of the flame configuration and a counterplot of our simulation results. We have a central main jet and pilot jet with different equivalent ratios of ammonia, hydrogen, nitrogen, air blends, and they are surrounded by co-flow of air. These flames exhibit local extinction properties, particularly in Flame F, which serve as a challenging validation case for the effectiveness and robustness of our DFOD net method. We first conducted direct integration simulations using LES with the Sigma subgrid scale model and a PSR TCI model on a structured hexahedral mesh with around 400 million cells. 4 million cells. We used 25 species, 100 reactions mechanism developed by Okafor, and also tested different turbulence generation methods for the at the main jet inlet. These the experiment results are not shown here by request from the original authors, but it can be seen through the comparison of we have temperature and the mass fraction of oxygen here. at different streamwise locations that we're able to predict local extinction and reignition events similar to experiment findings, and that, as shown in the figures below, flame F is sensitive to boundary conditions at the inlet of the main jet. We also found that in order to achieve better qualitative alignment with experiment data, the most effective way was to refine the mesh to near quasi-DNS requirements in the reaction zones, which will significantly increase computation costs. However, the finer grid shown here is probably over-refined in reaction zones and are too expensive. We plan to use a new mesh with more evenly distributed grid to continue our research. So this also showcases the acceleration speed-up potential of our DFOD method and brings about the question of scalability with larger meshes. To elaborate on our training data generation process in this case, we conducted simulations of one-dimensional premixed laminar flames, two-dimensional counterflow diffusion flames. In the series of laminar flames, we sampled equivalent ratios from 0.9 to 3, corresponding to the experiment configurations. And we also interpolated with air states to account for the equivalent ratios below 0.9. For the diffusion flames, we sampled counterflow streams of main jet conditions and co-flow conditions and covered strain rates near extinction limits. This low-dimensional data provides a rich training set for our DNN models, ensuring generality across different combustion scenarios. We validated our models through various tests before application in full-scale simulations. Here we show the results of laminar flame speeds in one-dimensional premixed laminar flames with different equivalence ratios. And in the middle, we have scalar descriptions of the flame front in two-dimensional counterflow diffusion flames and counter plots of temperature and vorticity in our two-dimensional HIT ignition. We were able to achieve great overall consistency with the results obtained by direct integration. These validations confirm that our DFOD models accurately predict both basic flame properties and complex interactions between turbulence and chemistry. As for DNN simulations of the COS flames, we currently only have preliminary results of flame D. Here we show the transient temperature field after around 4 flow-through times of flame D, and it can be seen that the development of flame shapes have been successfully predicted. We've only recently achieved satisfactory results in direct integration simulations in flame F, and we plan to apply our DNN models to flame F for further validation. And at last, we have a brief summary that DFOD-net DNN models consistently produces accurate CFD results. We were able to achieve high precision in predictions in lower dimensional both priori and posteriori tests. We have good applicability to ammonia and hydrogen fields and non-premixed scenarios. And we have preliminary success in COS flame simulations. As for some ideas of future work, we've listed them here, and we plan to open source the network training and deep flame interface, including the entire complete sampling process in the rest of this year. This is the end of my talk. Thank you for your time.
Thank you for your last talk. Any questions?
Thank you for a nice talk. This is Junjun from COST. So I have 2 questions. So the first one is for the DNN model. So solve the governing equation in CPU or GPU?
In our case, we solve the governing equations of CFD and CPU.
So this means you have data transfers from CPU to GPU.
Yes, yes, yes.
Is it cause some memory issues for like in the real jet frame simulation?
I don't think we've really encountered severe memory problems. We have sufficient like.
So how was the speed up for this flame F calculation?
This
I mean using
this one.
Yes, yes.
The speed up factor is about 10 to 15.
Oh, very promising results. Thank you.
Thank you.
Any other questions? Okay, I have one question from the online audience. They ask that where is the open source code for the DFODNet method? Can they get the code?
Well, thanks for the question. I've shown the GitHub repository link for Deep Flame, I think, over here. And as for our DFODNet source codes, we've still the GitHub repository is still in construction, and we plan to open source this in the rest of this year. And as for the specific link, you can follow this account on GitHub, this deep modeling account. We should also be, yeah, we can be found there.
Okay, thank you. Okay, thank you all guys. Let's close this seminar and thank you.